This conference will now be recorded.
Hey, Michaela, I just want to thank you for inviting me to present this material to you and to everyone at Veterans in Pain today. It's such great material. This is work I've been doing for the past 8 years now, both in the lab and then translated to clinical application, which is obviously the most gratifying part of it. But traumatic brain injury is such a, you know, misunderstood, underdiagnosed, and improperly treated condition. And from it, there's so many other issues that people experience in life related to their initial traumatic brain injury, or maybe even a traumatic brain injury that they didn't even know that they had. So look forward to giving you guys this presentation. Again, thanks for allowing me to present, and I hope you and everyone here finds it helpful and hopefully learns a thing or two. So let's move ahead here in these slides. And all right, so traumatic brain injury. Traumatic brain injury is basically anything that causes disruption in the brain. It can be slip and fall that causes the brain to be displaced beyond the cerebral spinal fluid that supports it in the brain or in the skull and crashes into the bony structure of the skull. This causes a disruption of the neurovasculature in the brain, damage to the neurons. When you get that, basically the neurons are damaged or trying to repair themselves, and so is the neurovasculature. I have a picture of Katrina here, so I kind of equate it to when the levees broke down and flooded the whole area. That's essentially what's happening in your brain with the blood vessels in your brain. Now the issue is the neurons take a long time to repair, but the neurovasculature can actually repair fairly quickly. Interestingly, there's a cyclical effect that then occurs where the neurovasculature repairs, but the neurons within the parenchyma of the injury are still emitting what we call a cytokine signal or a cell signal. And that cell signal is going from the neurons in the injured area up to the blood vessels. And these white blood cells, macrophages, neutrophils, and stem cells that are flowing along in the brain, they see that and they go to help the neurons. Well, the only way that the white blood cells can get through the blood-brain barrier to help the neurons once it's repaired is to basically reopen it, and they chew their way through. And they chew their way through, they disrupt the rebuilt blood-brain barrier, and you get this cyclical effect of inflammation from the neurons that take a long time to repair, the blood-brain barrier that's already repaired breaking again, white blood cells getting through, more inflammation occurring, blood-brain barrier repairing, then getting broken again, so on and so forth. And it's just kind of a never-ending cycle, especially if you're exposed to multiple repeat traumatic brain injuries, like a lot of people are. One slip and fall, you'll probably recover from it because our bodies are fairly resilient, especially if you're younger, but multiple can be pretty troubling. So I got into this research because football was obviously a big part of my life and interesting to me. And I remember back in summer of 2013, the NFL settled a $765 million lawsuit with its former players over the concussion issue. And that number later got upwardsly revised over $1 billion. So it was a pretty big deal. And these big star athletes were taking their lives and on all kinds of drugs to manage their symptoms. But something that people aren't exposed to, every Saturday and Sunday when they turn on their TV are military personnel. And I don't think people understand exactly how a concussion can occur. It doesn't necessarily mean you have to, bang your head into a rock or get hit with an explosive device directly. When there's a bomb that goes off, there's a massive amount of overpressure in the air. And that overpressure can do the exact same thing to your brain as, a middle linebacker or a running back running into each other head on, or you slipping on the tile when it's wet. And people don't understand that. They don't know how to then diagnose it because, hey, maybe a bomb went off and you have, shell shock, but you didn't actually get hit with anything. Or maybe you're training with explosive devices or automatic weapons. We know with concussion that they're additive. So you get a lot of small concussions over time. It can build up to one big concussion. Or if you're, training with explosive devices all the time, well, those are major mini concussions basically repeated over time, and those are additive. There's going to be serious side effects after that. And that was a huge issue with our military servicemen and women, and totally underdiagnosed, which is unfortunate. So like I said, I was interested in this because I played football. I'd see a lot of my friends and my buddies, teammates, they'd get a concussion, they just have to sit out until they got better. And kind of thought, hey, this is a little weird. Why can't we do something to take care of these people? So I went to college at Amherst College undergrad, but I was fortunate enough to do my master's at Louisiana Tech, and I started doing this research. I said, look, I want to study concussion. And I said, okay, first thing you need to learn is how to induce a concussion in an animal model. So we did this crazy stuff where we take a rat or mouse and drill a hole in its skull, expose it, glue a lure lock cap to its head, and then hook it up to this column of water. And we could control the exact pressure in the column of water to then flush this rat's brain with a saline solution to then create a very controlled and precise concussion. Believe it or not, this is common in the laboratory science field for inducing concussion. But if any of you guys on this call have ever known somebody that got their head flushed with saline solution, let me know. I've yet to meet anybody like that, so it seemed pretty silly to me. We did talk about explosive devices. This is another rat model that they'll do. They again drill a hole in the rat's head, put a little ball of TNT on top of it, and set it off and on fire. And I mean, this just is not totally analogous to what's going on. So I was lucky enough when I was looking for solutions to come across this device. Dr. Elliot Lander was using it in his urology practice. And it's called the Storz Deactor, and it's basically an acoustic shockwave device. So it takes acoustic energy and converts it, and it's used in orthopedics, urology, aesthetics. And we can take that device and we can basically, put it over a rat's head. And that acts and mimics the overpressure from an explosive device that you would see in a wartime setting. So that's what we did, and we were the first ones to do this, and we had to validate this model, which is not something I'm set out to do, but nevertheless we showed, hey, as we crank up the pressure, we can create motor skill deficits in these rats, and memory deficits in the rats as well. And we looked at the histology, and we showed that, hey, the greater the pressure that we create, the greater the infarct and injury that we could see histologically in the rats. So top left is no injury, top right is a mild injury, bottom left is moderate injury. You can see the infarct growing, and then bottom right is the largest injury that we had. So this was a scalable model, and we could see these dying and apoptotic unhealthy cells, and again, good scalable injury. So, but I'm not here to just mess with rats all day. We want to find a treatment option. And when you were looking at concussion and CTE, you looked at the treatment options. Well, there aren't any. They told you to go rest in a dark room until your symptoms went away. If you went to your doctor for any other injury or disease, or if you sprained your ankle and they said you just go rest in a dark room until it went away, you wouldn't go to a dark room. You'd go to another doctor. But this is what the top doctors were telling people to do. Maybe you take some Tylenol or anti-inflammatories, aspirin. Hyperbaric oxygen is something that became kind of exciting for a little while. I remember I went to a concussion congress, and they had a doctor from Stanford up there who worked with all the athletes, and he was going to give the latest breaking studies on how to treat concussion. And their big groundbreaking thing was, hey, we have our athletes come in the next day after they had their concussion and run for 30 minutes so we get their heart rate up above 100, 110 or 120 beats per minute. And that was it. You're like, what? Nothing else? That's all? So we'll kind of come back to that and say why I think that showed some good efficacy, but it's really just scratching the surface. So I had some experience with stem cells and knew that these things are anti-inflammatory and had some other pretty exciting properties, and maybe they could help with concussion. So that's what we set off to do. I'm not here to tell you that I was the first one to think of this. Plenty of other people have thought of treating traumatic brain injury with stem cells. People have used a host of allogenic cells, bone marrow, cord blood. But we worked with what's called stromal vascular fraction, and we thought that that could be one of the best things to go with. All the animal models showed really good results. So improved motor function, memory. They showed that the cells could actually replace neural cells that have been injured, and that the cells are anti-inflammatory and immune modulatory, which are all positive things that you want for concussion. So this is pretty good stuff. And we did a really simple study. So like I said, we worked with what's called stromal vascular fraction. Stromal vascular fraction are adipose-derived stem cells. It's a mixture of a bunch of cell types. So you have adipose-derived mesenchymal stem cells, hematopoietic stem cells. Hematopoietic means that they can form blood product, but these cells actually happen to be very angiogenic, which means they can turn into a blood vessel really well, which is really important for the pathology of a concussion. They also have pericytes and preadipocytes. All four of those cell types are progenitor stem cells. There are also some white blood cells, red blood cells, growth factors, exosomes in there, and it can be a healthy mix of cells. So all the cells that we worked with were fresh. They were harvested, prepared the same day that they were administered, and about 2 hours before they were administered. All the cells were labeled with fluorescent Q dots. This allowed us to then, after we gave the rats the cells, go back and try and find them in the body, see where they went, where they ended up homing into and lodging and getting stuck or whatnot. And they were all given via tail vein IV injection. So we wanted to start with the least invasive route of administration first. We had 3 different groups. One group, they all got the exact same concussion. One group was treated the day of that they got their concussion. The other group was treated 72 hours after. And the third group was treated with saline lactated ringer control group. So 2 with SVF, 1 same day, 1 72 hours after, and a control group that was treated the same day all with IV. So we characterized our cells using what's called flow cytometry. It allows you to basically see in a heterogeneous cell population what cells that you have very specifically, and we're able to see that we have about over 8% adipose-derived stem cells, 7.5% hematopoietic stem cells. So this is really good. And we trained these rats in all these different things, and we saw some really crazy results. When we gave SVF to the rats the day of their concussion, we saw no memory deficit whatsoever. Meanwhile, if we treated the rats at day 3 or just gave them IV saline, they didn't make a full recovery until 2 weeks later. So that was really astonishing. And then when we get to the motor skills test, again, if we treated the rats the day of with stem cells, we saw no sign of concussion whatsoever. And the rats that we treated at day 3, this red line here, they were back up to baseline the next day. Whereas the ones that were treated with the control saline, they didn't make a full recovery after 2 weeks. So something very interesting here, that if we can treat the concussion right away, we can basically ameliorate any of the symptoms of the concussion. And even if you're a little bit late, you're going to get better results than doing nothing at all, going to sit in your dark room. And these pictures are really speak volumes. As I said, we tagged all of the cells that we used, so we could go back and find them. And here we're looking at the left frontal cortex of the brain, and these glowing dots, these are stem cells. These are the stem cells that we tagged, and those cells that were administered 3 days after made it to the left frontal cortex in the brain, right where we delivered the acoustic shock wave injury. And that's great, but look at this. These were These are photos from the cells that were administered the day of. When you administer cells the day of, oh my God, they were all over the place. And I've got so many pictures like this. And all the people I worked with, they go, oh, there's no way, you're not going to find any cells. The cells don't home. They won't get there. That, they're going to get stuck in the lungs. No, these cells were all over the place. And it really, I think, does a great job to explain the memory and motor skills outcome from those cells that were administered the day of. So how did it happen? One of the really important things, I think, is that we used fresh cells. So these cells weren't culture expanded. They were brought from the clinic right over to the laboratory, and the study was done right away. Sometimes back in the day, especially when you were culture expanding cells will self-replicate, divide, become new stem cells, or they can differentiate into functional tissue. It's an important property of cells. You can put them on a plastic plate and give them the right environment, and they'll do this in the laboratory. But if you scrape the cells off the plate, it'll cause them to kind of elongate and become a little bit more rigid, as opposed to these nice round spherical kind of squishy cells that we like in reality. And these more elongated cells that are concocted in the lab, they can probably get stuck in the lungs, so they don't have as good of a migratory ability. But that's exactly what we saw, is these fresh stem cells do have a migratory ability. Think about it. We put these cells in the tail vein of the rat, which is about as far away from the brain as possible. They traveled all the way through the venous system, into the heart, back to the lungs, back to the heart, boom, up to the brain. We're able to find them there. So the cells are able to home in on sites of inflammation, which is really a powerful thing. And they have an immunomodulatory mechanism. So like I said, there's that cyclical thing where you have the white blood cells trying to go help the neurons, and they're breaking down the blood-brain barrier. The blood-brain barrier is being rebuilt, and then they're breaking it down again because the neurons take longer to heal. Well, stem cells can kind of suppress that. They can calm that down. And that's, I think, a large reason why you see return to normalcy in the motor skills test from the rats that were given cells at 72 hours. Is you have that huge anti-inflammatory effect, and that's going to allow people to recover and get back to normalcy much quicker. And so we were able to publish this material, and that was great. But then we took it to the next level, and we said, all right, look, a lot of people that are getting concussions are exposing themselves either through their work that they do or the sports that they play, and they're getting repeat concussions. So hey, let's do a study where we look at it. This is something really simple. Let's take two groups of rats. We'll give them the exact same concussion in the exact same location once a week, every week for 10 weeks. And half of them will get treated with 1 million expanded stem cells from the lab, and half of them will get treated with IV saline solution, so a control group. And we'll monitor for their memory and their motor skills. So this picture just goes to show that there are new techniques for isolating cells in the lab where they can be totally round and spherical and not elongated, which is great. This is what's called writing time. So when you give a rat a concussion, you flip it on its back and you see how long it takes for it to stand up on all 4 feet and walk away. And that's known as a writing time. You measure that. You can see a huge difference between the animals that were treated with stem cells versus the ones that were treated with saline, our control group. The control group, much longer writing time, whereas the ones that were treated with stem cells, their writing time stayed fairly consistent throughout the duration of this research. Fat rat is a happy rat, is a healthy rat. And those that were treated with stem cells weighed, I think, on average 10 grams more than those that were untreated or were treated with the control saline. But this is really the fun stuff. So let's look at the gross histology here and check out the brains. In this image, if you look at the left frontal cortex of the brain, upper left-hand corner, you'll see a huge infarct. This was the first brains I'm going to show you are the ones that were treated with saline. So our control group, you can see a huge infarct in the left frontal cortex of the brain, which is where we administered the traumatic brain injury, the acoustic shock wave. Again, in this one, you can see it very clearly. Left frontal cortex, you can see that infarct up there. It's pretty gross, pretty easy to see. Again, these were all treated with a saline solution, so our control. Now, this is the first one of our brains that was treated with cells. And this looks like a perfectly healthy, normal brain. I mean, this animal got the exact same concussion schedule as all the other ones. Only difference is it was treated with cells and not saline. Again, this brain looks totally healthy, normal, treated with cells and not saline. This one, you can see a little infarct in the top left, not as bad as the ones that were treated with saline. Again, a tiny little infarct in the top left, but overall looks fairly healthy compared to the other ones that we were looking at. This brain looks just fine. So it was pretty good. Now, the difference in this study versus the previous study, obviously the cells were culture expanded, but also we used human cells in an animal model, so we could go back and find them by doing what's called a human nucleus stain. Any cell with a human nucleus, the cells would be stained, and basically all the little black dots that you see in here, those are human nucleated cells. Those are the cells that we injected into the rat's brain, and voila, there they are. So look, I'm not here to just work with rats all day. The whole concept is, hey, let's see if something works in the lab, and then how can we translate it to the clinic? And that's what we did here. This was one of the first guys to receive cells for an acute concussion. The doctor that took care of him saw my presentation, and he was working with this gentleman who was in the NFL for 12 years, I believe, had 13 documented concussions, probably many more. This was a while back, so while he was a kicker, he was widely used as a tackling dummy during spring training and summer practices and whatnot. He was at his daughter's soccer practice, got hit in the back of the head with a ball, and was out cold, had to be airlifted to the nearby hospital, and just really didn't sound good when he called the doctor who treated him up. And the guy said, "Oh my God, like, you got a real bad concussion. You got to get in here right away. I saw this study with rats, and these stem cells might work." Okay, sure, let's try. So literally overnight, the guy apparently had a great response. I saw him a few months after he was treated and had this injury, and he came up to me and said, "Hey, thank you, but I got to tell you, I wake up scared every day now." And that's because since I retired from the NFL, I've been on anti-inflammatories, Vicodin, Percocets, sleeping pills, just to cope with the pain that I've had over a lifetime in this career. Since I had this injury and received cells, I haven't taken anything. And I wake up scared just because I know one day the pain's going to come back, and I don't know when that's going to be, but for now, this is great. And that was something that was pretty cool to hear. So that was our first story, and I work with a company called the Cell Surgical Network. It's essentially a group of doctors all across the U.S. and around the world. They all work together under what's called IRB, or Institutional Review Board approved protocols. And we study all of this stuff in the clinical application, keep an online database to record it. And here's 20 patients, 15 of which reported positive improvement after a TBI injury. This data is not the best in the world, because some of these patients had traumatic brain injury and were treated literally the next day. I know a couple of them personally, and some of them had severe TBI 5-10 years ago and were treated later. But there's really obviously encouraging results being seen here right off the bat. I have stroke up here because stroke is similar to concussion from a pathology standpoint, in that it's a disruption of the neurovasculature system. And our stroke patients respond pretty well to cell therapy, which is great. And through our database, we can look at different routes of administration. So on the left, you see IV deployment. We get a pretty good response compared to what's called intrathecal deployment, or into the lumbar cerebral spinal fluid. Now, is it necessarily fair? There are way fewer numbers for intrathecal versus intravenous deployment. And for all intents and purposes, the intrathecal deployments could be for more severe cases because it is a more difficult deployment technique than intravenous. But nevertheless, I think it's a really good sign that intravenous is yielding such good responses, and it's what we'd expect based on these studies, because we know that these cells can home to sites of inflammation, and that's exactly what's going on in the brain. Now, this is not a study that I was involved with, but it's one that I think is awesome and, and really cool to share. This is on using stem cells for alcoholics. So alcohol can be dependency, and it can be really difficult, but it's a cell injury that's occurring. Something's off in the brain that's causing people to continually consume alcohol. So this study took groups of rats, and they got all the rats addicted to alcohol, so that when they were given water, a choice between water or alcohol, all the rats chose water. Now, this first group on the top were given what's called an intracerebral injection. So the stem cells were administered directly into the brain. And if you look, the ones that received the stem cells, their intake of alcohol dropped precipitously. Whereas the ones that were given a control or saline into the brain, they continued to drink alcohol, and they didn't choose water instead. Funny enough, though, if you look down to the second row, they did the same study, except instead of injecting the cells directly into the brain, they injected them IV. And the same thing happened. The rats that got IV injection of stem cells chose water instead of alcohol, and the ones that got an IV injection of saline chose alcohol over water. So there's something about these cells that's hugely anti-inflammatory and can correct what's a cell injury. So really the take-home thing and the big kind of finding here is, hey, we have a lot of these veterans coming home from war and training and active service, and they've got PTSD, and they're being treated as though they're a purely psychologic condition. And I don't think that that's the case. Now, I've got this picture up here. It's an analogy, but it's obviously a pretty intense freeway interchange. And that's basically the way I think of the brain. You have all these different neural pathways that are connected in different ways, and it allows thoughts from one area to go to another. And it's all these electrical impulses that are, getting thoughts all over and across our brain. Well, when you're exposed to a blast, overpressure, I don't know if that's a bomb or automatic weapon that you're training with all the time, or hey, if you're working with jet engines, every time that jet engine goes off, that's a massive amount of overpressure, and that could be disrupting these neural pathways in your brain. And then you come back, and then there's this PTSD. Well, is that purely psychological, or is it physiological as well? The pathways are disrupted, which I'm convinced that they are. I think it's physiological as well as probably psychological. So instead of just trying to treat it as though it's purely psychological, I think you need to repair the cellular deficit before you can then try and take on this psychological aspects of it. And there's a great study out of the University of Pennsylvania that looked at people that had traumatic brain injury, and then looked at them as though they were either optimists or pessimists. Now, the pessimists actually reduced the amount of brain function that they had. I kind of think of it this way: if you're used to taking the same path to work every day, and all of a sudden there's an earthquake, and one of these overpasses break, and you all of a sudden you get stuck, the pessimist is going to say, damn it, damn it, damn it, damn it, damn it, like, why can't I go, why can't I go, why can't I go? The optimists, though, they showed after a concussion actually increased their brain function. More parts of their brain were starting to be used. So if that roadway breaks and the optimist says, oh, shoot, I can't go this way to work anymore, I'll just find another route. I'll travel some back roads or whatever, and I'll make it into the office on time. And all of a sudden, you see different parts of the brain start to light up. And I think that's exactly what's going on. Needless to say, at the end of the day, why, try and make yourself work harder when you can, or you should, repair the cellular injury? And that's essentially what we're trying to do. So we submitted a proposal to the United States Air Force, and we were selected last year. Unfortunately, you can see the dates right before COVID really blew up and hit. So shortly after, they said, hey, look, all of the stuff that we were going to fund that involved interpersonal interaction, which this project obviously did, we're going to put that on hold. So hopefully we'll be able to start this up soon again, but we want to look at people that were exposed to blasts, have PTSD, pretty severe, and we want to try and repair the cellular pathways that have been damaged and injured. So I'm really optimistic about this. I'm excited about it. I think it's fantastic research, and hopefully change the way that our veterans can come home and live a healthy, happy lifestyle, and not have to deal with the frustrations and difficulties, impairments that come along with PTSD. And I think that comes from it just being misdiagnosed, misunderstood, and improperly treated. So this was some fun work, and I appreciate the opportunity to share it with everybody. I hope it was helpful or insightful, and hopefully stuff that you haven't necessarily heard before. I don't know that it's widely out there and widely available, but it's pretty cool stuff. So anyway, if you guys have any questions for me, I'd be more than happy to field them. I think you can just, if you can pass them along to Michaela, she can forward them along to me, and I can, respond to you guys personally, and be happy to help however I can. But thank you for joining. Thanks for inviting me to speak and giving me the time to share this work that I've been working on for about 8 years now with everybody. So thanks a lot, and enjoy the rest of your day. Have a good one.